today we are going to talk about the concepts of two-port networks, and we will be seeing why we will be using those. So the essential concept behind a two-port network and the idea of using it really relies on the fact that you want to, in general, when you're thinking about a circuit, you want to be dealing with, if you're dealing with a large circuit, you want to be able to break it up into smaller units that you can deal with. And something that commonly happens a lot is that you have a chain of blocks, you have a cascade of blocks, and these cascade of blocks, basically the output of the first block is the input to the next block, and so on and so forth. And in those particular cases, the two-port networks are especially useful. So let's talk about the two-port networks and see where they come from. I mean, so we are going to talk about two-port networks. But before we even talk about that, let's talk about the basic concept of one port which we've used. The one port, or a two-terminal device, is essentially a box that has two terminals. And if you have these only two terminals, and if you're in the circuit domain, in other words, if you don't have any, everything is much smaller than the wavelength, then this current that goes in has to be the same at any instance as the current that comes out. This comes from the fact that basically circuit domain corresponds to having an infinite speed of light. And if you think about this, this is just a one port. Now, if you want to go to a two port, if you want to generalize this concept, you want to have two sets of terminals, two pairs of terminals, more accurately, that basically you have currents going in from the first terminal I1 and V1, and currents going in I2 and V2. Now, in general, if you have four terminals, you will not necessarily satisfy this condition of having I1 being the same as this I1, because what you really need is that the algebraic sum of all these four currents being the same. So this is a much more strict constraint, and that's what makes a two-port really. So for something to be two-port, this constraint needs to be satisfied, namely that this current and that current are the same. For the current, the ingoing and outgoing current for the one port are the same. So these are both I1, and these two currents are also the same. So these both have to be I2. Now, there are different ways for this to be satisfied. In a trivial and rather useless way, in general or less general, if you had, for example, a device attached, a two-terminal element, like a resistor or an inductor or a capacitor attached here, this will guarantee that you have something like this. But this is rather useless, because if you have something like this, there's no coupling between the ports, and it kind of like renders the use of two ports obvious or useless. So more important, the other way that this constraint can be satisfied is basically by applying an external source to it. So if you apply an external source, let's say for example a current source, I1, then this guarantees that these two will be the same. Same thing if you apply a voltage source. So if I apply a voltage source here, V2, then what happens is that you have no choice by having these, having these two currents being the same. So in other words, what makes a real two-port is something that has these two currents and these two currents being equal, but this constraint can be enforced externally or internally. So as long as this constraint is satisfied, then you do have a two-port. Now, if you want to think about two ports, there are different ways to think about them, and it's a way of breaking the circuit, because like I said, these are what we call sometimes sub-circuits. So in general, if you want to describe something like this, you could say that as long as the circuit is linear time invariant, so you're talking about LTI circuits, you're thinking about a linear combination of these currents and voltages having a general relation. So in the most general case, you have A1 V1 plus A2 V2 plus B1 I1 plus B2 I2 plus some constant C1 equals 0. And there will be two sets of equations describing these. So there will be another set, A3 V3 plus A4 V4 plus B3 I1, these are I1 and of course I1 and I2. The V1 and V2, there's no V3 and V4. And B4 I2 plus C2 equals 0. So these would be the equations describing this two-port. So this is just the right number of equations to describe it, and also to allow for the external elements that are attached, be it a source or a load or some sort of a resistor or impedance or what have you, being able to impose its own constraints. Because this basically sets, you have four variables here, 2 voltages and 2 currents, and you have 2 equations. So that leaves 2 more degrees of freedom that would be enforced by what is attached to the input and what's attached to the output. So this is just the right number of equations, so you don't need more or less. Now, in general, when you think about it, what is the thing that causes the C1 and C2? If you think about that, it is really the sources, the independent sources inside the network. Now, let's assume that there are no independent sources inside. So no independent sources in the 2-port. In that case, that would basically imply that C1 and C2 are both 0. So then you will have something that will have no offset, essentially. Those linear lines describing these things, or linear hyperplanes in this case, describing these equations, they all go through the origin eventually. So in those cases, essentially, you will have the same set of equations except for the fact that you don't have the C. So if I rewrite those, I can write it as A1 V1 plus A2 V2, A3 V1 plus A4 V2 plus B1 I1 plus B2 I2 equals 0, and B3 I1 plus B4 I2 is 0. Now you can see, you can recognize these forms, right? Probably if you look at these carefully, this should remind you of something, which is basically the matrix multiplication. So you can actually represent this entire thing, as a matrix A multiplied by a vector V plus or being equal in this case, and you can move these terms to the other side, a matrix B and a vector I, where matrix A is A1, A2, A3, A4. Matrix B is negative B1, negative B2, negative B3, negative B4. And V and I are, so V is the vector of V1 and V2. I wrote it as capital V. And then you also have the vector I, which is basically I1 and I2. So this is the equation describing this in the compact form, this relationship. So if you think about this, then you can actually try to write, if you were to write, for example, the voltage in terms of the current, how would you go about doing that? Well, you can see from this equation, it can be easily seen, that what you need is really to apply the inverse of A to both sides. But that also assumes that inverse of A exists. So one assumption that you make, you know that for the inverse, for A to be invertible, the determinant should be non-zero. It should be non-singular. And if that is the case, then, so this is an assumption you're making, then V can be written as A inverse B matrices applied on I. Now, we can combine these two, look at the combined matrix, and we call it the matrix Z, or the Z matrix, where Z will have, the matrix Z has 4 components. Matrix Z is Z11, Z12, Z21, and Z22. And this describes this 2-port network completely, as long as it's an LTI and it has no source, no independent sources inside. So if you have something like that, then you can actually think about it. And by the way, one side note is that this has nothing to do with the Z matrix that you get when you do mesh analysis. They just have the same notation, but they have nothing in common in general, if you think about it. They're the same. They're not the same thing. They're 2 different things. So they should not be confused. Now, and the interesting thing about this is that if you look at this expression, or you can actually even write this expression, this matrix form in an expanded fashion, you can actually write it as V1 equals Z11 I1 plus Z12 I2, and you can write V2 as Z21 I1 plus Z22 I2. And in essence, what we are saying is that this is a compact form of, this is an expanded form of this compact expression. Now, if you look at this carefully, this provides us with a way to actually evaluate and determine and characterize a two-port network. How? Well, let's say I'm interested in knowing what Z11 is. Well, if I'm trying to find Z11, I can determine it by looking at this and setting I2 to 0 and looking at the ratio of V1 over Y1. So it's basically V1 over I1 when I2 equals 0. So what does this mean? What's the meaning of this thing? If you think about it, you will see that essentially, from a circuit perspective, it corresponds to the case where you apply a current source, I1, to port 1, and you measure the voltage of the port. So you apply an I1 stimulus, and you measure the voltage V1, and you look at the ratio while, and this is an important thing, while what's happening to the second port. What does this condition imply? When you say I2 is 0, what is the network that produces a current of 0? It is an open circuit, right? So if you think about this, so for this I2 to be 0, this has to be an open circuit. So basically, this I2 equals 0 means port 2 is open circuit. So this is how you evaluate this. This is if you wanted, if you had a black box and you know that's an LTI system with no sources inside and you wanted to view it as a two-port, what you can do, you basically apply a current and you measure the voltage here while you keep the other port open. And this is kind of measurements, these are basically network measurements. Sometimes actually we perform these measurements. We may not do it exactly the same way, but we actually derive a lot of things. There's actually a device called, a piece of equipment called network analyzer that looks at all of these different parameters, including Z parameters, and the other ones that we'll talk about a little bit later. So that's basically Z11. How about the other ones? Let's say, how about how do you evaluate Z12 or Z21, let's say? What is Z21? Well, let's look at Z21. Z21 is the ratio of V2 over I1 when I2 is 0. So we can write it as V2 over I1 when I2 is 0. So what does that mean? It means that you apply an I1, but instead this time, instead of measuring V1 here, you measure V2 there. While it's open circuit, while port 2 is open circuited. And you look at this, evaluate this ratio, and that would be your Z21. Now, and you can do similar things for the other two, and once you evaluate all four, you have characterized this two-port completely. So this is basically the two-port we are trying to evaluate, or characterize more accurately. So how about the other two? Well, it's going to be pretty straightforward. So how about Z12? Z12 is going to be ratio of V1 over I2 when I1 equals 0. So what does that mean? How do you do that? Well, in this case, you're applying a current source stimulus to the second port. So now your current source is sitting here. You're applying it here. So you're applying an I2 current. So this condition doesn't hold. Actually, I2 was pointing this way anyway. So this is I2. And then what do you do for the first port? For first port, you leave it open circuit. You set I1 to 0. So basically, that means that to guarantee that I1 is 0, you need to leave it open circuit. So you have it open circuited here. So this is port 1 open circuit. And what you do, you apply the I2 and measure V1 here. And finally, for Z22, what you do, you measure V2 over I2 when I1 is 0, which basically is, again, the same condition. You keep port 1 open circuited, but this time you apply an I2 and you measure this V2. So when you do these four things, you have completely characterized this two-port network. So what does that mean? So what do we do with these things? Well, it means that if you have a black box with a whole bunch of components in it, for example, and you don't know what is inside, or you can always characterize it with these four parameters. So if you rewrite this set of equations, so what we have is that we know V1 is Z11 I1 plus Z12 I2, and then we know that V2 is Z21 I1 plus Z22 I2, which can be also written in the matrix form or compact way. But this corresponds to, so now let's say you know what Z11, Z12, Z21, and Z22 are. Now, if you do, can we come up with an equivalent circuit? Something that would behave exactly like this. And the analogy, think about it the way we used Thevenin and Norton equivalence earlier to say, okay, well, whatever is inside that box, from a circuit perspective, from the current and voltage perspective, it's equivalent to this. So how do we do that? Well, can we create a, what should we put inside this box to behave like the other box, but we use only these 4 parameters? Well, if you think about it, this looks like a resistor, right? Or an impedance, more accurately. So you have an impedance times the current giving you voltage. So if this is I1, if I put an element Z11 in series, that would produce this term, because the voltage across that element would be Z11 I1. Now, I need to have something else to produce this term, right? I need another voltage to be generated like this. But now this voltage is dependent on a current of the other port, on the current of this port, I2. So what kind of element would do that? It would be a dependent current source, right? So if you think about a dependent current source, I'm saying dependent voltage source, not dependent current source, dependent voltage, because you're trying to generate a voltage. So this will have to be a Z12 I2. So if I put a dependent voltage source here, now I have 2 voltages. This one, which is Z11 I1 by Ohm's law, and this voltage, which is Z12 I2. So this dependent voltage source is producing that, and you're getting the sum of those 2 voltages at the input. So your overall V1 would be sum of these 2, which would be exactly this equation. And now that you've done this, the other side should be pretty straightforward. To generalize by symmetry, you can say that there should be another one here, should be a dependent source here, and an impedance. This would be Z22, this would be Z21 V1. And as you can see, this would produce the second equation. So this is the equivalent model for a 2-port that you've characterized. So you can say, I really don't care what's inside that box, as long as I've characterized it. In general, this characterization would be done as a function of frequency. So you do it at frequency. These are complex quantities. So you basically characterize it as a 4 complex quantity as a function of frequency, and then use that value, those values, to find what your system is. And you can use this model going forward. So you can actually, this would be a box that you can replace that box with. Now, a lot of times, actually, these 2 ports are used to evaluate, they're very useful for characterizing 3-terminal devices. So examples of those, we haven't really gotten into details of those, is, for example, a transistor, a MOSFET, or a bipolar. If you think about a MOSFET or a bipolar, if it's biased at some level, there is some sort of a common terminal, the ground. In this case, it would be the source of an NMOS. And then you have the input, which is usually applied to the gate, and an output, which is taken from the drain. Usually there has to be some sort of an internal bias into this thing, but we are not going to get into that right now. Let's say you're characterizing this device when it's operating and biased at the right place. So if you think about this, really what you have a common terminal, and then as long as you can apply the right source at the input, and then you characterize it at the output, you can actually characterize it with a 2-port. And in those cases, in some of these cases, basically your 2-port becomes a special kind of a 2-port, where basically you are connecting these 2 terminals to each other to form the third terminal. So this becomes a terminal, input terminal, output terminal, and the common or ground terminal when you do this characterization. And you can do different kind of characterization. We haven't talked about other ones. We have just talked about the Z parameters. So that's a common thing to do. But generally, when you do your characterization, that's what happens. So let's do a couple of quick examples, simple examples, and then see where that leads us. So let's pick an example. The first example would be, let's say you have a network that looks like this. So you have a simple resistor here, resistor R. So this is your 2-port. So let's say this is our 2-port, and we want to find what the Z parameters are. So let's go through our procedure that we described earlier and see how we apply. So this is port 1, V1. This is current I1, current I2, and voltage V2. So this is port 1 and port 2. Okay, so if you want to determine what is Z11, What is Z11? How do we, well, we said it was the ratio of V1 over I1 when I2 was 0. Basically, when you leave the second port open circuit. If you do that, then if you look at this, you can easily see that this is basically the ratio of V1 to I1 is the resistance seen across here when the other port is open, which is basically R. So this term Z11 would be R. How about Z12? Or Z21? Let's do the Z21 first. Z21. What would Z21 be? Well, by definition, we have V2 over I1 when I2 is 0. So it's still the same condition. You leave the second port open, and then you're applying an I1 here, and you want to know what this voltage is. So if you apply an I1, V2 is going to be I1 times R, because all of that current has to go through the resistor R, and therefore the ratio of V2 over I1 is going to be just, again, resistor R. And then you can, of course, at this point, you can probably by symmetry say that the other two are also the same. But very quickly to do that very quickly, you can look at Z22, for example, which would be V2 over I2 when I1 is 0. And that would be basically you're applying a current source at the output. And then here, current source I2. And first you are measuring the voltage across here. Again, when this one is open circuited, which is basically gives you the ratio, would be giving the resistor. And by the same token, if you apply this current and look at this voltage on the other side, still you will see the same voltage because these are now connected, where Z12 becomes also, which is V1 over I2 when I1 is 0, is also R. So the Z matrix in this example is simply R, 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 and R. Okay? So it's not that complicated by itself. Now, let's try another example and see what that tells us. So if you think about it, let's go back and let's try a slightly different case. So this was a parallel case. So let's do a series case. So let's say our two-port network is just a series resistor coming across. R. I1, I2, and then you enforce that, so the other side is true. The same thing is true for these other terminals too. So this is V1 and V2. So what do we get in this case? Well, let's evaluate it. Let's evaluate Z11. So to evaluate Z11, you have to apply current source I1 here and leave the other terminal open and find Z11, which is the ratio of V1 over I1 when I2 is 0. But what is that value? Does that work? If you think about it. If you think about it for a second and see if it works. Well, we clearly have a problem, right? Because if you think about this, you will see that the current, you're trying to inject a current into this thing while the other end is open. So since I2 and I1 are essentially the same with a minus sign, you cannot force an I1 into this thing. And it would basically produce an infinite voltage and things of that sort here, which would not be appropriate. So basically, this would become an undefined thing, or it goes to infinity and things of that sort. So what's happening? Something is failing here. And what is failing? When things generally fail, when some things don't work, usually you have to go back to the assumptions you've made to lead to them. So what was the assumption? What were the assumptions that we made to get to the Z parameters? Let's go back and revisit them very quickly. You remember when we were defining the Z parameters, right? We said that this matrix A needs to be inverted. And of course, that means that it had to be invertible. And for it to be invertible, its determinant needs to be non-zero. So let's see what the determinant of that A matrix is in this example. So let's find out. So there are two equations that describe this, right? There are two equations, and what are those two equations? One is the relationship between I1 and I2. So what is that relationship? So if you think about that, I1 and I2 are both going in, so the sum of those, the algebraic sum, should be 0. Because one is basically I1 and I2 are the same with opposite polarities, right? So I1 is negative I2. The other relationship is the relationship between V2 and V1 and I1, right, or I2. So you can say V1, this voltage, is V2 plus the voltage drop across this resistor, which would be I1 or Ri1. So if you take this and bring it back to this original form that we wrote for A and B, it's this form. So you want to write it in this form and find what the A and B matrices are. Let's see what we get. So if we do that, we can actually write this in this form. We can write it as, so for the first equation, we get 0 times V1 plus 0 times V2 plus I1 minus I2 equals 0. And for the second one, you get 1, or I'm not going to write the 1, so I'm going to write V1 minus V2 minus Ri1 plus 0 times I2 is 0. So let's write the A and B matrices. So A matrix is 0, 0, 1, minus 1. 0, 0, 1, minus 1. And the B matrix is going to be negative 1, because it has a negative of those, so plus 1, R, and 0. So now we had to invert matrix A. So to invert something first, it has to look at its determinant, and its determinant needs to be non-zero. So what is the determinant of A in this case? No. So you can see the problem, right? The problem is that the determinant of A is 0, so A is singular. It cannot be inverted. And that's why we ran into a problem. So Z parameters really don't exist for this two-port, and you cannot describe it with Z parameters with this particular one. So that is a problem for that. So that's one thing. There are interesting properties. There are a couple of definitions that are important for Z parameters in general. If you're thinking about Z parameters, one of the things that you need to think about, there's an important definition which is called the reciprocity. So we call a two-port network reciprocal when Z12 is equal to Z21. So that's the definition of the reciprocity. Basically, when this matrix, the Z matrix, is symmetrical, right? Now, why does that matter? Because that actually leads to some interesting properties. And usually, it can basically lead to some useful descriptions of the circuit. So let's say that you're starting with a reciprocal network. So let's say you are starting with a reciprocal network. And see what we can say about it. So the assumption here is that Z12 equals Z21, right? So I'm going to write something first. So let's look at what the so-called T matrix, or sometimes they call it a Y matrix, depending on how you draw it. Because if you take these two and kind of move them up, it looks like a Y, capital Y, or this way, obviously looking like a T. So let's say you have a ZA, ZB, and ZC. So let's look at the two-port associated with this. So let's find what the Z11, Z12, Z21, Z22 are for this. So it's relatively straightforward. Z11 is essentially the impedance you see here, because the ratio of this voltage, the voltage of this port to the current of this port, when the other port is open. So it's basically ratio of V1 over I1 when I2 is 0. And if you look at that, it's obviously just this impedance plus that impedance, because that's the impedance that you will see here. So it would be ZA plus ZC. Now, how about Z21, which would be the ratio of V2 over I1 when I2 is 0. So if you apply an I1 here, right, and then keep this open and look at this voltage, well, this voltage is the same as that voltage, because there's no current flowing through this resistor when it's an open circuit, so the voltage across it is 0. And this voltage is basically what? Is this current, all of this current will flow through ZC, so it would be I1 times ZC divided by I1. So that would give you ZC. Now similarly, if you do it for the other port, what happens is that you will get a Z22, which this time would be ZB plus ZC, which is the impedance you see across here when you open circuit this side. and then Z12, which would, again, by the same expression, would be ZC. So you have defined all these 4. Now, why is this useful? So let's think about this. Let's say that, let me try to take one more step. Let us take another step and say, let's solve for ZA, ZB, and ZC in terms of. So in general, you don't have enough information. But now, if we take this assumption, then you can say this is the same thing as Z12. And you can see that in this case, this is indeed reciprocal because Z12 and Z21 are the same. So if that's the case, let's solve for ZA, ZB, and ZC. So it's a very straightforward calculation because, for example, from this and that, you can determine that ZA is Z11 minus Z12. If you subtract this from that, Z11 minus Z12 produces ZA. And ZB is going to be Z22 minus Z12. And then ZC is going to be Z12 itself. So if you have these 3 parameters, what you have is this. Now, what does this tell you? It tells you something very important. It tells you that if you have a reciprocal network, if your network is reciprocal, you can describe any reciprocal network with a T network. There's an equivalent circuit for it, which is just a T. And the parameters of that T are Z11 minus Z12, Z22 minus Z12, and Z12 itself. So it means that if you've characterized a reciprocal network, if you have characterized a 2-port network, and you found that it's reciprocal, you know somehow that it's reciprocal, you can replace it with this resistive T network. And all you need to do is to make this, or more generally, impedance, right? So basically, this can be just impedances. So to emphasize that they're impedances, I will make just little tiny boxes. So if you have characterized this to be reciprocal, and you know that's reciprocal, this impedance would be Z11 minus Z12, this impedance would be Z12, and this would be Z22 minus Z12. And this is a pretty useful thing. Because then you can, this is basically how you determine, for example, the Y delta conversion that we did before and things of that sort. So I can do a numerical example for you. Let's do actually a kind of like maybe a simple delta Y one. So let's say you're starting with a network, a resistive network, which is essentially a delta network like this. And let's make this, I don't know, let's say make this 3 ohms, 3 ohms. And to convert it to a T, I need to determine its Z parameters first. And if I have the Z parameters, I can use this to calculate. So what is Z11 in this case? Well, Z11 is the impedance you see across here, really, when the other port is open. Port 1 when port 2 is open. So what do you see? You see 6 ohms in parallel with 3 ohms, which gives you 2 ohms. Right? And then you have the Z22, which by symmetry and also doing the same thing, that would be also 2 ohms. You have a Z12, which is what? Well, it's the voltage you see across here when there's if you apply a current source, Z21 really, where you apply a current source here, I1, and the voltage you see here across V2. So what is that? If you apply a current source here, you have a current divider between a 3 ohm and 6 ohm. So you get 1/3 on this branch and 2/3 on this branch. And the 1/3 of the I1 that goes through gets multiplied by 3 ohms, so you get 1. So you get 1 ohm. And similarly, if you apply it the other way, Z12, you will see is also 1 ohms. So the Z matrix for this looks like, if I drop the units, it would be 2, 2, 1, 1, all in ohms, obviously. So this is the Z matrix. Now, if I take this, if I take it and use it in this model, in this picture, what do I get? What do we get? So let's see. So you have a T model, right? So this one should be Z11 minus Z12. So it's 2 ohms minus 1 ohm. So it's 1 ohm. This is going to be Z22 minus Z12. So Z22 minus Z12, again, it would be 1 ohms. And this would be just simply Z12, which is, again, 1 ohm. So this network is equivalent to that network. So you can see that we perform the delta y conversion here. Now, one question is, what makes a network reciprocal? How do you make sure it's reciprocal? Is there a way for us to know if something is reciprocal, or how can you get a non-reciprocal? Generally speaking, if you have no sources, well, we said already that we don't have any independent sources, but if, let's say, you have no dependent sources, if your network is purely made of resistors, inductors, and capacitors, then your network becomes reciprocal. And if you have a reciprocal network, then you can always do this, and you can always represent it like this if you have the z parameters, which is, again, a useful thing because it allows you to understand it. Now, how about, you may say, well, what does a non-reciprocal network look like? Well, you can make a simple one, right? For example, I can make one that is a one resistor here, 1 ohm, and then if I put a dependent source here, so let's say if this is I1, this is, let's say, 100 I1. Okay? And then if you try to characterize this, let's find the z parameters for this. So this would be I2. What are the z parameters for this? Well, the first step is apply a current source here, I1. And then, so Z11 would be the ratio of V1 over I1 when I2 is 0, when you leave it open circuit. So if you do that, well, you have a little bit of a problem because now you have nothing going through here. So maybe I can add a resistor here to make this a little bit more realistic. But so let's add a 1 ohm resistor here. So now, in this case, you apply a current of I1. All of it goes through the resistor. The voltage across here, V1, is going to be basically 1 times I1, which basically produces 1 ohm. So that's Z11. How about Z21? The voltage that you produce on the other side when you apply this I1, still keeping the other side open. Now, in this case, I'm applying an I1. This current is I1. So this is 100 times I1. And that current is going through this resistor. So what is the voltage that's produced here? The voltage that's produced here, if you are careful, you will see that the current is flowing this way, so it will have the opposite polarity. So this voltage would be 100 times I1. So this is negative 100 times I1. Divided by I1 would be negative 100. And now, so we've determined Z11 and Z12. So let's now determine Z22 and Z12. Okay? So Z22 is now, for Z22 and Z12, you need to apply a current of I2 and then measure V2. Right? So what do we get? Well, if this is open, now we've kept I1 to 0, what happens to this current source? This current source is also 0 because I1 is 0, so the value of a current source is 0. And what is the current source with the value of 0? If it's 0 current, it's an open circuit, so this doesn't exist. So what you end up with, you have this current going through this resistor, so you will get 1 ohm. And then how about Z12? Well, we are applying this current here, and we are looking at what the voltage would be here. Do we produce any voltage here? No, this circuit is isolated from that because you put the current through here. This current is still 0, so all of it goes through here. There's no reason for any voltage to be generated here, so that would be 0. So what you will see is that the Z matrix looks like 1, negative 100, 0, and 1. And you clearly see that these two not being equal makes it non-reciprocal. So this is something that you cannot represent as this T network. And it's a more general network. So this is an example of a non-reciprocal network. Because, again, you can see easily it's done by using a dependent current source. In this case, basically, it's a current-dependent current source. This, by the way, would be a kind of like a model for a bipolar transistor. This resistor would be larger, but and that resistor too, depending on the current, but generally speaking, this kind of model. So now we still had a problem, if you remember, right? I mean, if you go back to this expression, in this example, we saw that we had no z parameters. And that arose from the fact that what we were doing in our original matrix calculation that we had an A times V equals B times I. And what we did to determine the z parameters was to calculate the inverse of A, which in this case didn't exist, and apply it to B. So what if the A cannot be inverted? Are we done? Is there no way to characterize this thing? Or are there other ways to characterize it? Well, if you think about it, probably you can say, well, why don't we invert B and apply it to the other side and see what we get? Well, if we do that, then we get I equals B inverse. And of course, for this to have to be valid, the determinant of B now needs to be non-zero. And apply it to A and apply it to V. Now, this is how you get the Y parameters. Characterize the two-port with the Y parameters. Again, these Y parameters have nothing to do with the Y matrix that you get out of the nodal analysis necessarily. So this is not the same thing. It's just a similar notation. So let's look at that. Let's look at the Y parameters and see how they look like. So let's start with that. Let's see. So if we do that, then the expressions, so if we are writing basically this time I as Y on V, which again, if you write an expanded form, what you will get is I1 equals Y11 V1 plus Y12 V2. I2 is Y21 V1 plus Y22 V2. Okay? So what does this mean? What does it look like? Well, it's similar to z parameters, except for the fact that now they need to be evaluated differently. So for example, if you want to determine y11, what do we do? y11 is I1 over V1 when V2 is 0. What does it mean for V2 to be 0? Let's look at the two-port again. So this is I1 V1 and I2 V2, right? And this is our two-port. So we are applying now this time we are applying, the stimulus, which is always in the denominator, is a voltage source of V1. And then we are measuring I1. But what do we do to the other port? We say V2 is 0. What is the thing that's identically, what's the element that's identically produces 0 voltage? It's a short circuit, right? So if you have a short circuit here, forces V2 to be 0. So it means that for this measurement, what you do, you short circuit the other port for Y measurements, which is different from Z measurements, right? And when you short circuit this, you measure the ratio of this voltage to this current, and that would be, or this current to this voltage more accurately, and that would be your Y11. How about the other Y's? How about let's say Y21. What is Y21? How do we evaluate that? Well, if you look at the equations, you will see that Y21 is I2 divided by V1 when V2 is 0. So how do we evaluate that? So it's the same deal. You apply a V1 here, you short circuit the other side, but now instead you monitor the current through this short circuit. And the ratio of this current through the short circuit on the other port, so this is the current that this voltage induces on the other side when it's short circuited, divided by the voltage that produces the Y21. And similarly, so now if you want to look at, for example, Y22 and Y12, what you will do, Y22 would be V2, or rather I2 over V2 when V1 is 0, and I12 would be I1 over V2 when V1 is 0, which basically means, this means port 2 is short-circuited, 2 short-circuited. This means port 1 is short-circuited, and 1 short-circuited. Which basically means, so for determining these two, what you do, now this time instead of this, you apply a voltage source of V2 to the other side, and short-circuit this and measure this current I1 for this calculation, and measure this current I2 for this calculation. Now, you can see from this that it is actually a different calculation because it is a different quantity in general. And if I ask you, what is the relationship between the Y matrix and Z matrix, or more specifically, is there a direct relationship between Y11 and Z11? You should be careful not to say that Y11 is 1 over Z11. Because think about it, although they are measured from the same port, so when you measure the Y11, you're measuring it from the same port. And what happens here is that you're applying a voltage source of V1 and measuring I1, and in the other case you are applying a current source of I1 and measuring the value of V1, but you are changing the network that's seen, because in the Z case you had this open circuited, in the Y case you have to short circuit this. So this changes the impedance seen, so Y11 and Z11 are not directly related at all times. So you may say, well, is there any relationship between them? Yes, if you think about our notation of A and B matrices, that leads us to a conclusion. Remember, we had AV was BI, and in the case of Z matrix, we wrote it as V equals A inverse B times I. So this became Z I. And in the case of Y matrix, we wrote it as I equals B inverse A times V, which basically means this was a Y times a V. Now, if you look at these two expressions, you can clearly see that the entire matrix Z is Y inverse. So if we ask you, for example, if I ask you, or if you want to find out what Y11 is, so Y11 would really come from the inverse of Z matrix, or Z11 if you want to kind of make it more consistent with this expression that we've written here. So we have to invert the Y matrix. So how do we invert a matrix? We look at the cofactors. So the cofactor for the element 1, 1 is element 2, 2. So it would be Y22 divided by the determinant, which would be Y11, Y22 minus Y12, Y21. So this would be the relationship between, for example, Z11 and Y11. And you can see Z11 depends on all 4 Y parameters. And this is true for all 4 of them. You can calculate it. This is a simple matrix inversion that you need to think about. So you need to be careful not to make that mistake or that confusion there. Okay. So these two sets of parameters are quite useful, but there's another set of parameters that's also quite very useful, and then we would like to talk about those a little bit now. Now, the thing with, so this was the Y parameters and Z parameters we talked about. The next set of parameters, we are interested in a set of parameters that allow us to look at multiple 2 ports. In this case, I'm going to show just 2. And you can capture and allow you to characterize each one of them independently and get the aggregate response in a straightforward fashion. So let's say this is port 1 of the first one. Let's call it T and T prime. And then the voltage across this is going to be V1 plus V1. And then you have I2, and then you have V2 across that. And then this one will have its own input current, I1 prime and V1 prime. And then you have a V2 prime and I2 prime. So the question is that, can we come up with a set of parameters that would allow you to characterize this in a meaningful and cascadable fashion? So for that to happen, you have to think about the following. You have to think how can you relate these parameters to the other ones? Now, and this leads to the so-called chain or transmission parameters. So what we are talking about is chain or transmission parameters. They are also known as A, B, C, D parameters. So how does this work? So we want to define, let's say, a set of variables. Let's say the input variables versus the output variables. And you want to define one in terms of the other. So to do that, we really need to write this in a form that's more conducive to this. So instead of having voltages on one side and currents on the other side, we can try to write our expression in terms of, let's say, the input variables, the variables of port 1, V1 and I1, in terms of the variables of the output, V2 and I2. Now, if you do it this way, the idea here is that for the next network, you have a V1 prime and I1 prime that would be expressed in terms of its output variables, V2 prime and I2 prime. And the key is to see if you can actually plug this in here and have these two matrices back to back, so you can actually get the product of these matrices to describe the overall aggregate response of the combination of these two boxes. Now, for that to happen, these two have to be equal. So if you look at it carefully, let's see if they are. So V1 prime and V2, they are the same voltages, so this is not a problem. But if you look at it, there's a little bit of a subtlety here, because you can see that I2 is going this way and I1 prime is going this way. So I1 prime is really I2, negative I2. So we can, if we define our transmission parameters or ABCD parameters this way, then you can directly plug this into the next one, and it continues working for as many of these as you have. So if we do it this way, we define these four parameters of this matrix as A, B, C, and D, and then we can characterize them fully by looking at these parameters and determining what they are. So let's find out what they are. So for example, A is what? So A times V1, you have A V2 equals V1 if you set I2 to 0. So A is essentially the ratio of V1 to V2 when I2 is 0. In other words, port 2 is open circuited. So how do you evaluate that? You apply a voltage to port 2. You leave port you apply a voltage to port 2, and then you set the parameters for you apply voltage to port 1, and you look at voltage at port 2, and you look at that ratio, the inverse ratio, and then evaluate that. Then you get B is evaluated the same way, right? B is going to be, so we have B times negative I2 is V1. So B becomes negative V1 over I2 when V2 is 0. In other words, port 2 is short-circuited. So here, you apply a voltage V1, you measure the current through a short circuit. You short-circuit the second part, and you look at that current, and you look at the inverse ratio, V1 over I2. And similarly, C, you can actually do the same thing. You can say, well, C is going to be I1 over V2 when when I2 is 0, which basically means that port 2 is open circuited. So what you do, you apply current I1 and measure voltage V2, and you calculate the inverse ratio when the second port is open circuited. And D, which would be the ratio of negative I1 over I2 when V2 is 0, is basically means that you apply current I1, you short circuit port 2, and you look at the current through that, and you look at the inverse ratio. So this is actually pretty useful, because then it allows you to cascade them. So let's look at a couple of simple examples of this and see how we can use it. So as a first example, consider this simple network. So let's consider a network where you have an admittance Y connected in parallel. So this is I1, I2, V1, and V2. And let's find the parameters. So A, by definition, from the definition we had, is V1 over V2 when I2 is 0. So what is it? When I2 is 0 means that port 2 is open circuited. We apply a voltage V1 and look at V2. Now, if you apply voltage V1 and you look at V2, it's going to be the same because they're connected directly. So this is going to be 1. How about B? What's the parameter B? Parameter B is negative V1 over I2 when V2 is 0. In other words, you short circuit it for V2 to be 0. And you're applying a voltage V1 here, and you have a short circuit on the other side. So obviously, if you have a voltage source across a short circuit, the current would be infinity. In this case, in fact, would be negative infinity because it's going in the other direction. But anyway, the ratio of V1 to I2 then becomes 0 because you have an infinity in the denominator. Now, if you go to the C parameter is defined by I1 over V2, which when I2 is 0, which basically means that you have now an open circuit on the other side. You apply an I1, and you want to measure the voltage across here. So if you apply I1 and you measure that voltage, what do you see? The voltage is going to be essentially, so if this is current I1, and you're measuring voltage V2. So it's the current times its impedance, or the current divided by Y naught. So in this case, this would simply be Y naught, because that would be the ratio of the current here to the voltage that it induces. And for D, parameter D, which is defined as negative I1 over I2 when V2 is 0, you basically apply a current I1 and you short circuit this, and then what do you get? If you apply a current I1, this current would be I1. So I2 would be negative I1, and therefore this ratio becomes 1 because of that additional minus sign here. So now the ABCD matrix for this thing is going to be simply 1, 0, Y0, and 1. So that's what you get. Now let's do another one, a slightly different, kind of like somewhat of a dual of this, in the sense that now let's say you have a series impedance Z naught, and then you have an I1 and I2 and V1 and V2, and we want to characterize this one in terms of ABCD parameter. Now you can imagine why we are trying to characterize these two, but if you can't, then you'll see it in a few minutes. So let's see. What are the parameters? So A is going to be again V1 over V2 when I2 is 0. Basically, this is open circuited. I'm applying a voltage V1, measuring V2. So the ratio of these two would be 1 because they're the same. Because there's kind of like there's no current flowing, they would be the same, 1. How about B? B is negative V1 over I2 when V2 is 0. So I'm applying a voltage V1. Now this time V2 is 0, which basically means that I'm short circuiting this. And I'm measuring the current, I2. The current is going to be negative V1 divided by Z naught because it's going to be going in this direction, and this is the I2. And that minus sign cancels that, so that ratio simply becomes Z naught. Now how about C? C is I1 over V2 when I2 is 0. In other words, again, when you keep this open circuited, and I1 over V2 is going to be what? So you apply a current source and you look at the voltage here. So if you apply a current source, the voltage here is going to be infinity because you're putting a current into an open circuit. So this V2 is going to be infinity, and this is the finite quantity, so this becomes 0. And then D, which would be negative I1 over I2 when V2 is 0, is basically means that V2 is 0 means that we short circuit the other side, we apply current here, and this current, these two currents will be the same with a change in polarity. So I2 will be negative I1, and there's a minus sign here, so it becomes 1. So this produces a ABCD matrix that's 1, Z naught, 0, and 1. Okay, so now we have these two, and let's see how we can use these for something even more interesting. The idea here is that we saw that the ABCD matrices, they are cascaded. So one of the things you could actually do is to use this to find the transfer function of a more complex network. So let's say you have an input, you have a resistor of 1 ohm, you have a capacitor of 1 farad, you have an inductor of 1 Henry, and then you have another resistor of 1/2 of ohms. And then this is your output voltage, let's say, V out, or VO for short. And this is VI. So the question is, how do we find the ratio of V out to V in? So what we can use it in the same format as the ABCD parameters or the transmission parameters. So we have a VI, and let's call this II, and then we can express it in terms of the transmission to each one of them. But now we can actually, instead of thinking about this as one giant thing, we can break it into 4 2-ports. So we can say each one of these green boxes is a 2-port whose output is the input to the next one. So this is a 1 farad capacitor here. So what do we get? Well, what is the transmission? What is the ABCD matrix for the first one? Well, we have developed this. Now you can see why we've developed this, because you can actually break that up into series and parallel elements. So the first element, which is the resistor, is the series element. So Z0 is 1. So we'll get a 1, 1, 0, 1. This describes that first network. Now, what does the second network give you? So you have a parallel element of 1 farad capacitor, which is this thing. So what is Y of a capacitor? It's CS. So in this case, it's going to be just S. So it's going to be 1, 0, S, 1. How about the third one? It's an inductor in series. So it's a Z0. The Z of an inductor is LS, which basically, in this case, L being 1, it becomes S. So it becomes a 1, S, 0, 1. And the last element being a resistor, again, in parallel. So it's an admittance of 2, because it's the resistance of 1/2, or conductance of 2. So basically, we'll get a 1, 2, 0, 1. And that would be times V out and negative I out, where I out is this. Now, in this case, of course, if you have an open circuit at the output, I out would be 0. So, but what we need to do first is to calculate the product of these 4 matrices. And it's a pretty straightforward evaluation. We can actually do it in pairs. So we can calculate the product of these two. So this times that gives you S plus 1. This times that gives you a 1. This times that gives you an S. And this times that gives you a 1. And here between these two, you have this times that gives you 2S plus 1. This times that gives you S. This times that gives you 2. And this times that gives you a 1. And then now you have to calculate the product of these two. So basically what you get is that you get this times that. So you get 2s squared plus, so it would be this, so times that. So you get 2s squared plus 3s plus 1 plus from here and another 2 from this product. So you get plus 3. This times that gives you s squared plus s plus 1. This times that, which would give you 2s squared plus s plus the 2 from this one and that one. And then you get this times that, which basically gives you s squared plus 1 times VO negative IO is V in I in. Now, if we are only interested in V out, V in relationship, and we know IO is 0, so we know if it's open circuit, so I out is 0, what you will get is basically this term by itself times VO is V in. So V in is going to be 2s squared plus 3s plus 3 times VO, which basically means that the transfer function for this thing is going to be, which is defined as VO over V in, is going to be 1 over 2s squared plus 3s plus 3. And you can see that using the ABCD parameters, we have calculated this transfer function accurately. Now, these are not the only parameters. There are other parameters. For example, one set of parameters that are very, very useful and commonly used for characterizing 2 ports is the S parameters. So the idea of S parameters is that now instead of having a short or open, which happens a lot in these cases, you can see we get shorts and opens in definitions of these things, you want to make something that's neither short nor an open. And the reason for that is that when you have making a short or an open at very high frequencies is very difficult to get a very precise short or an open, because any short will have some capacitances, and any open will have some capacitance, and any short will have some inductance. So as you go to higher frequency, it will have a sufficiently large impedance to cause a problem. Now, in those cases, you actually want to deal with a situation where your source has a fixed, well-defined impedance, and often you want it to be a resistive one. A very common value for that is 50 ohms. That's why a lot of high-frequency measurements are done with 50 ohms. So in S parameters, what you do, you look at the ratios of the reflected power from the port to the incident power. So for example, if you have a port you're looking at, you basically have an incident power, and then you look at the reflected power coming out of here. The ratio of that reflected power to the incident power, for example, when it's properly normalized, is called the S11. Or you look at incident power from here and the power that comes out of the other one, you can think about as reflected out of the other port, and the ratio of that reflected power out of the second port to the first one would be S21. And so on and so forth. So those parameters are defined, and they are used a lot in high frequency and microwave systems, which you can study on your own. We are not going to get into the details of that. But again, there are many different ways to characterize two ports. But the bottom line of all of those is that it's a way of creating these subcircuits and being able to use them in cascade and characterizing them without trying to get all the details of what is going inside. So that's it for the two-port parameters. And if there are no questions, we'll move forward.